Hello, I'm Tim Lichtenberg from the University of Oxford, and in this video I will present a brief summary of our research project, Bifurcation of Planetary Building Blocks during Solar System Formation, in collaboration with Joanna Drążkowska, Maria Schönbächler, Gregor Gorlabek, and Thomas Hans. Our research is motivated by the question of how observed substructure in protoplanetary disks may influence the chemical and isotopic abundances of formed planets. In particular, the relation between planetary accretion and the so-called isotopic dichotomy and chemical fractionation that we observe between the present-day inner and the outer solar system. To begin with, let me introduce two independent lines of evidence from related scientific fields that give us constraints on this question. The plots here present evidence for temporal fragmentation of the planet formation process, from both exoplanetary systems and from the early solar system. On the left-hand side, we see stellar mass versus mass in solids, in either the dust component of disks or in exoplanetary cores. The plot shows that the observed total dust mass in disks decreases substantially from class 0 to 1 to 2. In class 2 systems, there is not sufficient dust mass anymore to explain the masses of exoplanetary systems. This suggests that the dust component may get incorporated into larger objects relatively early during the evolution of the disks. Planet formation starts early. The right plot shows complementary evidence for the early solar system from the timing of iron core formation in planetesimals, the so-called parent bodies of the meteorites. It shows that these planetesimals formed iron cores very early during the solar accretion disk. To match the measured core formation ages, the planetesimal families from which the respective iron meteorites are derived from must have formed nearly at the same time as the formation of calcium aluminum-rich inclusions, potentially as early as the class 0 or 1 phase of the solar system. From radiometric dating, we have additional evidence for protracted finish of the accretion process for Earth and Mars, showing that the proto-Earth likely accreted over several tens of millions of years, much longer than the accretion disk lived. In addition to this temporal information, we have evidence about the spatial fragmentation of the planet formation process. In disks, we observe substructure in the dust component as early as the class 1 disk phase. For the solar system, we also have evidence for spatial fragmentation from meteoritics, here shown in chromium versus titanium isotope space, the so-called isotopic dichotomy in neutron-rich supernova-derived isotopes, which separates the non-carbonaceous, or NC, and the carbonaceous, or CC, planetary reservoirs. In this research project, we investigated if multiple stages of planetesimal formation and their resulting geophysical evolution can be a potential mechanism to explain the observed trends. To do so, we used an astrophysical model of the disk build-up phase and quantified the compositional evolution of the planetesimal reservoirs that formed during the class 1 to the class 2 disk stage. In this scenario, the protosun accretes from the surrounding molecular cloud, and the disk is built up from the inside out. The qualitative evolution of the solid material in the scenario is illustrated in this sketch. Solids are in dust grains. Inside the snowline, water is in the vapor phase. Outside of the snowline, water is in the ice phase, and therefore the solid density is enhanced and dust grains coagulate more efficiently. When they grow, the aerodynamic drag from the surrounding gas becomes larger. Therefore, the drift velocity toward the protosun increases. When they cross the water ice line, they dehydrate, their sizes decrease, their speed reduces, and they drift therefore slower. This leads to a dust pileup, or traffic jam, at the location of the snowline and facilitates planetesimal formation by the streaming instability mechanism. This happens on a timescale of about 10 to the 5 years. In addition to the traffic jam effect, the so-called cold finger effect is operating. Water vapor from the inside of the snowline diffuses outward and refreezes onto grains just outside the snowline, which facilitates planetesimal formation by enhancing the solid surface density. This happens on a timescale of about 10 to the 3 years. The disk simulation we make use of in this work was published in 2018 in Astronomy and Astrophysics by Dr. Joanna Drążkowska and Professor Kees Dulmont. Please consult their paper if you are interested in further details about these simulations, but we also cover the main ingredients in the supplementary information of the present work. Here you see a video of the buildup of 2 consecutive planetesimal formation bursts in this disk and dust coagulation scenario. You see the movement of the snow line from the infall stage to the class 2 stage. 2 subsequent planetesimal reservoirs form, which differ in their formation times and orbital spacing. The first planetesimal reservoir forms mostly due to the cold finger effect. Let's call this reservoir 1. The second planetesimal formation burst, let's call it reservoir 2, forms later and with a substantially higher total mass, mostly due to the traffic jam effect. This has substantial implications for the internal evolution of these bodies, because the earliest planetesimals were internally heated from the decay of the short-lived radioisotope aluminum-26. This is shown here on the left-hand side, in log units of watts per kilogram of silicate material relative to the formation of calcium-aluminum-rich inclusions. Aluminum-26 decay was the primary heat source of the earliest planetesimals, driving internal core formation and volatile release on a timescale that is comparable to the planetary accretion process. This process is sensitive to the accretion time of planetary bodies because the half-life time of aluminum-26 is only of about 700,000 years. Geophysical models of the internal evolution of planetesimals, such as this on the right-hand side, can help us to quantify the compositional influence this may have on the deviation between reservoir 1 and reservoir 2 in the disk simulation. The plot on the left shows the internal heating regimes of planetesimals as a function of planetesimal radius and formation time after CAIs from the streaming instability. You see the highest mean temperature integrated over an interval of 5 million years of evolution, showing that large and early formed planetesimals can become so hot that their rock component starts to melt. We were here especially interested in 2 compositional mechanisms that can relate planetesimal evolution to the evidence from laboratory analysis of meteorites. These are internal hydrothermal activity and core formation in planetesimals. The colored lines shown here are associated with these thermochemical scenarios of internal compositional evolution. If you have an initial water ice-rich planetesimal, then this water ice will melt. The body goes through a phase of internal hydrothermal circulation. The formed hydrous rock phase will eventually decompose again when it becomes too hot for them to be stable. These stages are illustrated in H1 and H2 and occur at the heating peaks of the lines on the left. Planetesimals that become even hotter can form iron cores, either due to the so-called percolation or rainout of iron droplets in internal magma oceans. These stages are indicated with C1 and C2 on the left and right. Using these models, we compute the time-dependent evolution of the 2 planetesimal populations that are formed in the disk simulation. This relates the astrophysical formation environment to the thermochemical evolution of planetesimals. The inner solar system, or reservoir 1 here, experiences high internal processing, whereas reservoir 2 experiences only low internal processing due to the difference in formation time. The time-dependent evolution is shown on the left side as a function of time after CAIs and fraction of birth planetesimal population. Reservoir 1 produces a peak of iron core formation at about 1 million years. Reservoir 2 produces a peak at about 3 to 4 million years. On top, you see the ages of metal silicate segregation in the NC and CC record from meteorite measurements. In our simulation, reservoir 1 reproduces the clustering of the ages within the uncertainties in the NC reservoir. Reservoir 2 reproduces the clustering of the ages within the uncertainties in the CC reservoir. This slide shows a similar comparison for hydrothermal activity. Reservoir 2 produces a peak at about 4 to 5 million years, which reproduces the clustering of aqueous alteration ages in the CC record. In addition to the compositional inventory of the inner and outer solar system, the simulations are relevant for the distinction between the NC and CC isotope reservoirs. The observed isotope dichotomy is a puzzle, because in principle aerodynamic drift of pebbles should have homogenized the solar system quickly. Somehow this did not happen, because we can tell apart individual bodies from different orbits based on their nucleosynthetic fingerprints. Therefore, this drift must have been stopped or hindered somehow. At the moment, the most often discussed hypothesis for the separation mechanism is an early formed Jupiter core. We here aim to present a potential alternative mechanism to initiate the observed dichotomy. To do this, in the context of the disk scenario I explained earlier, we quantify the pebble flux at 2 and 15 AU. This is what you see in the bottom right here. The pebble flux at 2 AU is the red line and the pebble flux at 15 AU is shown in blue. These orbits are roughly representative of reservoir 1 or reservoir 2. Both lines from the left side plot correspond to the pebble flux at 2 and 15 AU on the bottom right plot. Initially, the pebble flux is roughly similar in both reservoirs, but over time it substantially deviates from each other. This is because the dust mass from the outer solar system is preferentially incorporated into reservoir 2 and contributes to the accretion of the outer solar system planets. This suggests a potential explanation for the isotope dichotomy. If there's initial heterogeneity in the isotope composition of the inner and outer disk, as evidenced by meteorite measurements suggests, then this will be preserved, because the material from the outer solar system does not reach the inner solar system efficiently. Additionally, this has implications for the growth mode of protoplanets. We contrast the efficiency of planetary growth either due to planetesimal accretion or pebble accretion. This is shown on the bottom right plot for 2 and 15 AU again, which corresponds to the pebble fluxes from the top plot here that I just discussed. The solid lines represent the timescale for growth of birth-sized planetesimals from pebble accretion at 2 and 15 AU. The dashed lines show the timescale for planetesimal collisional accretion. The plot indicates that the early phase in our simulation is dominated by collisional growth, then transitions into a pebble-dominated phase, and finally to a pebble-starved or collision-dominated phase. This is because the pebble flux in the inner solar system is substantially decreased by up to 2 orders of magnitude toward the end phases of the disk lifetime. This illustration summarizes the scenario of early solar system accretion that we derive from our simulations. During the infall phase, the disk grows from the surrounding molecular cloud. The initial infall is enriched in supernova-derived isotopes, but transitions to a depleted composition. The snow line moves first outward, then inward again. Due to the snow line tech and accompanying dust evolution, 2 planetesimal populations are formed and the isotopes in both reservoirs do not remix completely. The first planetesimals form the inner solar system, the second population forms in the outer solar system later and at wider orbits. Because of the difference in formation time, these 2 populations evolve to a different composition. The inner solar system dries out and quickly forms iron cores, while the outer solar system experiences a protracted onset of accretion. The inner solar system planets undergo a brief intermediate phase, during which the protoplanets likely accrete a substantial amount of dry pebbles, but the pebble flux decreases again toward the final disk phases. The secular and spatial variation of disk physics, planetesimal formation, growth stages, and geophysical evolution of the protoplanets in this scenario offer an explanation for the inventory and trends of volatile elements in the inner versus the outer solar system, the difference in mass budget, and the observed isotopic deviations. To summarize, the inner solar system starts accreting first, but experiences protracted growth with a heterogeneous growth mode which goes from collision-dominated at first to pebble-dominated and then pebble-starved during the final disk phases. The compositional and isotope dichotomy in the solar system we observe today are a result of the spatially and temporally distinct planetesimal formation bursts, which are built up first in the inner and then in the outer solar system, and the subsequent geophysical evolution from radiogenic heating. This suggests a volatile accretion sequence that starts from volatile depleted material, transitions to a dry phase, and then to being dominated by volatile rich material toward the end stages of accretion after the disk phase. To bring this new scenario for the formation of the solar system in context, we suggest that the specific composition of the inner terrestrial planets is a direct result of the accretion pathway of the planets, with the disk evolution, the mode of growth, and the geophysical evolution of the protoplanets during accretion as key physical variables. The simulations make a number of predictions that relate the mechanisms to observations of circumstellar disks, exoplanet composition statistics, and geochemical signatures in solar system planetary materials. We hope that our work on the formation of the solar system can contribute to further improve our understanding of our own origins and the distribution of planets like Earth in the galaxy. We will be happy to discuss any of this with you, so please do not hesitate to reach out to our author team with questions or comments. Thank you very much for your time and interest.